Okay, so I think we're ready to get started. So we got 2 lectures left. I kind of anticipate we are going to go into Friday's lecture. Sadly, I'm so sorry, but that's it. I guess I could talk really fast today and get it all done, but I'm not sure I really could. So I did start to post some practice material for the final exam. I got some stuff up today. I did, I think I mentioned this before, we've made some changes in Physics 1051 over the last couple of years to make it more suitable for its intent. That means the old exams that I posted, they're a little bit out of date. So I did post some old exams. I went through and I scribbled out everything that we don't do in 1051 anymore. So the problems that are left behind are representative of stuff you could see, but the new material is not on those old exams. So I would certainly not advise you to only study from those old exams. It's not going to give you the whole story. As you're studying, I would say your first resource should be the lectures. The reason I talk about it in class is because it's important, and if it's important, it's what goes on the test. So, you know, lectures first, then your assignments and problem sessions, then you can look at those old exams. I did post a review sheet. I made that up within the last 12 months for this course. That review sheet is probably better than the old exams. But people do pester me for old exams, so there they are. Use them if you want to. It's kind of up to you. I still haven't written the exam yet, so I still can't tell you that much about it. As soon as I write it, I'll be able to give you the details. That's it. So does anybody have any questions?
When you write the exam, are you going to post the, when you finish writing the exam, are you going to post the formula sheet that we're going to be given?
Yeah, formula sheet and cover sheet. So you'll be able to see the format and all the equations you'll have with you.
Okay.
Yeah. Okie dokie. So let's get started on today. Last day I said I'd make up a couple of videos to make the examples that we did last time just a little bit more accessible. So I did make those and I posted them. The links are there with the after class lectures and all the notes are posted as well. So anybody who found last day's kind of a little bit too much, the extra examples should help. So the first thing we'll get into today is talking about some of the applications of the fact that you can get a magnetic field from a current carrying wire. And you maybe saw a little hint of this in the lab when you made your DC motor. So the first one that's pretty cool is an electromagnet. I was going to sort of get a battery and the stuff to make an electromagnet to bring into class, but then I ran out of time, so I've got a video instead. So an electromagnet is when you wrap a wire around a huge piece of metal, which is normally not magnetic. You put the current through the wire, that creates a magnetic field, and it turns the piece of metal in the center into a magnet. That's what an electromagnet is. You might have done that like in an elementary school science project, maybe. That could be some people. Anyway, the good thing about those is you can do stuff like this. So he just picked up an engine from out of a car. I think he goes for the fridge next.
Yeah, that's pretty darn neat.
Right? So if you had a bunch of friends with you, you could probably lift all those things, but it wouldn't be very easy. So they do this stuff with electromagnets. So it just makes it easier to pick stuff up and can do a lot of work. Okay, back to here. Another one, when we have a long string of wire and we put it into a set of coils, you might imagine something like a slinky. When you put the current through the wire, you get a magnetic field around the wire. When it's all coiled, it turns out that the magnetic field goes down through the center of the wire, and it's uniform inside and it's zero outside. And this is called a solenoid. So when you make your coils of wire, you can get this strong uniform magnetic field. This can be very useful in applications where you want a strong uniform magnetic field. And a medical application would be an MRI unit. So inside your body, you have lots of little electric and magnetic fields. To do some sort of medical testing, often they want to read those fields. So to read them, they put you in a giant solenoid with one of these fields, and then they can read the screen from what happens there. So that's an application of this stuff. Okay, questions? So I think next, we're going to start a new topic, sort of new topic. Let's do a demo first, and then we'll think about these things as we go through our topic. So this demo, it probably has a name. We just call it the jumping rings. So this is basically a big electromagnet. It's got a solid iron core. It's really heavy. It's got coils of wire right here, and I'm going to plug it in. When I plug it in, the current runs through the coils. It makes a magnetic field like we had right there. You might ask yourself, what does it mean that I'm plugging it in? Kind of this current versus what comes out of a battery. It switches back and forth, right? It's an alternating current.
How would that affect the recording?
How would it affect what?
The recording.
I guess we'll find out, won't we? So I'm going to put this little ring on. And I'm going to turn the current on. And let's see what happens. So I'll turn the power on. Okay, that's pretty neat, right? This is a little aluminum ring. This is not magnetic. It won't stick to a magnet. I can use a bigger one if I want. The bigger one is less impressive, which is why I don't do it first. Okay, it'll still jump, but it's heavier, so not as much. And put on this little ring again. Okay, so when I do this with kids, I get them to turn it on, and then I was like, oh, did you break it? And of course, they didn't break it. So what we're going to get into, I don't think people can see this very well. Let me see if I can put it here. Here's the two rings I put on it. This one jumped and this one didn't. See the difference in them? Yeah, at least one person sees that. Okay, so we're going to think about why this matters. This one's got a little cut in it. Okay, so let's keep this in our heads as we go through, and then we could come back to the jumping rings after we talk about some of the theory. The theory that we're going to talk about also explains how a transformer works. So these are the things we're going to be talking about here. Lots of real applications here that are super useful in our lives today. So next, last day we talked about this. When we put a current through a wire, if we bring a compass close by, it starts to deflect, tells us that current carrying wire made a magnetic field. We talked about it being big circles. We found the directions and the directions at different points and fields to different wires. So we did a lot of that stuff. Michael Faraday came along, and he was very instrumental in this field. He did a lot. And Faraday asked, well, if this current carrying wire makes a magnetic field, is the flip side true? Does a magnetic field create a current? That's a good question, right? So if the current can make the field, does the field make a current? The answer to this question, why don't we look at it first, actually. So what I've got here, let's see Faraday's experiment. What I've got here is a giant galvanometer. This is just like the multimeters you use in the lab. This side's a little better. The only difference is it's a lot older. This thing is older than I am. It's been around in the department forever. But it does the same function. I've got it hooked up here to read potential difference. Okay, so I've got it hooked up to read voltage. It's a voltmeter. If it can read potential difference, we know if we have a potential difference, we also have a current. So it's kind of a measure of the same thing. What I have here is my coil of wire. This doesn't do anything. It's not hooked up to a power supply. It's just a coil of wire. And you can see that there's zero potential now. This is a stack of rare earth magnets. It's a pretty strong magnetic field. I'm going to put the field near the coil of wire. Okay, so that deflects. Okay, you should really look more amazed at this point. So I'm generating electricity from waving a magnet. Okay, that's pretty cool. We can see some different stuff. If I push it in slowly, I'm getting a small field. and it deflects one way. If I pull it out slowly the other way, I'm getting a small deflection. If I go fast, you get a big one, and then the other way. If I put it in and I just rotate it, kind of don't see any action there, so it's moving in and out. So if you move a magnetic field, you can generate current. This is clean energy, right? You figure out how to harness this, do it without greenhouse gases, you have just saved the planet. You know, there's a good goal for you, right? Nobel Prize, billions of dollars, right? Saving the earth. So there's something for you to work on. So this is what Faraday studied, right? You change the magnetic field. It does have to change. I have to move it in and out. You change it, you will get current. So there's Faraday's effect.
Isn't that how basic generators work?
Yeah, it is the function of a generator. So this was Faraday's question, and the answer to this question is yes, if the magnetic field changes. Okay. I think that's kind of like magic. That's what is so cool. So let's take this and let's see if we can understand how it works.
Can we define changes a bit more? Because like technically, that stack of magnets, like,
Yeah.
nothing about that stack was actually changing. It was more so like the way it was relating to the coil.
Yep, you're absolutely right. We are getting there. The thing that has to change is magnetic flux, which is the strength of the field compared to the area where it is. Okay, so we're coming.
Cool.
Yeah.
Cool.
So let's take a version to try and explain Faraday's effect. So let's start simple. Let's put a conducting bar, so it's a piece of metal. We'll put it in a magnetic field, and we are going to pull the bar to the right. So this is our setup. Let's start to ask what happens with that bar. So let's not limit ourselves to positive charges. Let's ask what happens to the charges in the bar. So our conducting bar is full of charges. We know that in a conductor, charges are free to move. So as we pull our bar to the right, the charges will feel a magnetic force because we have charges moving in a magnetic field. We know that the magnetic force, FV, is equal to QV cross B. So the magnitude of the magnetic force is going to be QVB. We're moving everything perpendicularly, so QVB times sine of 90 degrees is just QVB. The direction of the force, we can use our right-hand rule. If V is this way, B is this way, the force on a positive charge would point upwards. On a positive charge, FB is up. On a negative charge, the force is in the opposite direction. FB is down. So we can put that on our picture. We can put in a negative charge. So if all the positive charges are pushed up and the negative charges are pushed down, it means we get the top end to be positive and the bottom end to be negative. So our magnetic force results in positive charge moves up and negative charge moves down. The positives are up and the negatives are down. It means the charges have separated. So we've got a positive end here, a negative end here. When we have that separation of charge, we get an electric field. So it induces an electric field. So pulling the slider in that magnetic field induces an electric field. So this results in an induced electric field. And I say induced because it only happens because we've pulled the bar, right? We've induced that thing to happen. If we have an electric field over some distance, we also get a potential difference. So it also results in an induced potential difference. This induced potential difference is always called the EMF with a symbol of epsilon. This induced potential, this induced EMF, the same as any other potential, is the electric field times the distance. Okay, so we get this induced potential, which is what we could measure on a galvanometer. We get this only because we've moved the bar. So the motion is important, so you have to move it through the magnetic field. You good to hear? Okay, let's see if we can figure out how big these induced fields are. So how big is the induced potential? So we move the bar to the right, we get our positive charges feeling a force that points up, that gets them to move up. Our negative charges feel the force that points down, that gets them to drift down, that makes the electric field that points from the positive towards the negative. There's the electric field. We did all this on the last slide. So now our charges are feeling both a magnetic force and an electric force. Okay, so these charges are in an electric field, right? So they feel an electric force, and they're moving in a magnetic field, so they feel a magnetic force. They're experiencing two forces here. So the charges will reach a steady state. And when they reach a steady state, that means they're going to stop moving up or down. They'll do that when the net force on each charge is equal to 0. So any little charge in there, plus or minus. So a plus charge will have a magnetic force that points up and an electric force that points down. When that net force is 0, those charges will stop drifting up or down, right? And then it will be in a steady state. So that means FB minus FE equals 0. Our magnetic force had the magnitude of QVB. Our electric force has a magnitude of Q times E. So that tells us that QVB equals QE. The charges divide out. V times B equals the electric field. Okay, so there's a relationship between the electric field, the induced electric field, and the magnetic field it's sitting in. And it's related through the velocity that we pull it through by. You good to hear? Okay. Our question was, how big is the potential? Now that we know the field, we can find the potential difference. So electric field is potential difference divided by the length, or the distance of the separation of the charges. So our induced potential is electric field times the length, V times B times F. So if we pull that bar in the magnetic field, we'll get a potential difference induced across the two ends. That's the speed times the magnetic field times the length of the bar. You'll be able to measure the potential difference across the two ends. This part okay? All right, so this you might say, okay, fine, is this very useful? The thing that's useful is if we hook this up to a circuit. Okay, so if we turn this into a circuit, then our potential difference means we're going to get a current flowing, which is what we saw over there. We get the current flowing. So let's get to that part next. So we're going to take our conducting bar that we've just been looking at. It's got a length L. And we're going to put it on the conducting rails. So it's got length L. It's on conducting rails. Those are the gray bits here. They have resistance R. And we're going to set it in this magnetic field that points into the page. That's B. Okay, so this is only different from what we did before in that now we've put it in a full circuit. We've got it on conducting rails. So let's go through that process again. We're going to pull the bar to the right. So it's got a velocity to the right. Okay, so this is us pulling it, you know, whether it's by a rope or our hand or whatever machine we apply. So we're pulling it to the right. The positive charges will start to move up. So that's the motion of the positive charge. It's going to come to this branch. It will go around here, 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 and here. So the charges will flow around that circuit. That means we have a current flow in the circuit. So the positive charges move up. That means there's a counterclockwise current, and that current is induced in the circuit. So that flow of charge happens because we move the bar. That makes it feel a magnetic force that makes it move around. So we're getting that induced current. We already said what the potential difference was. So now we're going to use this expression for potential difference in Ohm's law, V equals IR, and see if we can calculate that induced current. Okay, so now that we know the potential, we know the resistance, we should be able to find the current. Ohm's law says that V equals IR, that's the form we're used to looking at. That means our current I is our potential, we called that epsilon for EMF, divided by the resistance. And this is our induced potential. And that induced potential is B times L times V divided by the resistance. So this is the size of current that we will get in that circuit. So this is current induced by the motion of the bar. All right, so we know that we're going to get them moving around because each of those charges feels a magnetic force. So let's start to ask, what's happening with the forces in this bar? So let's kind of do a force analysis. So the magnetic force is equal to, and let's talk about the force on this bar right here. So we know the force on each of those little charges. That's what makes them move around the circuit. We've got the bar moving. The bar is carrying the current. It's moving in a magnetic field, so it's going to feel a magnetic force. Maybe seeing how all this stuff is really cyclical, right? So all this stuff is really tied together. And this is kind of how we get to the thinking that electric and magnetic fields are not really separable because it just goes around in one big circle. So hopefully we're going to get to talk about that just before we have to quit. Okay, so the magnetic force on the bar is equal to the current induced in the bar times its length crossed with the magnetic field that it's sitting in. So let's see if we can figure out the direction of that force. In this bar, the current flows upwards, the magnetic field is into the page, so the force is to the left. So the induced magnetic force on this is to the left. We already said that we are pulling it to the right. So we can put that on there if we wish. There's the force of us pulling. So what we see is that we're pulling it to the left. This induced magnetic force, we're pulling it to the right. This induced magnetic force is to the left. This induced magnetic force will always oppose the motion. Okay, so that's kind of interesting. We'll always get something induced that opposes what we're doing to it. So this induced force let's see. if we can balance those forces, if we get a constant velocity, then we know that those forces have to be equal. And we have at least a couple of examples where we're going to work through that. Yeah, for sure. Okay, let's take one step further, because I love how all this stuff just goes around. So we've pulled the bar to the right. The magnetic forces make the charge flow around the circuit. The flowing charge is a current. This bar is a current-carrying wire in a magnetic field, so it feels a magnetic force. The other thing we know about current-carrying wires is that they create magnetic fields, right? So there's a current flowing through this bar. This creates a magnetic field. Put your thumb in the direction of the current. See, on this side, we're getting a field that comes right out of the page. Right? So just moving it creates a current, which creates a new field. So the result of the current in the bar is it induces a new magnetic field. If you wanted, you could calculate that. This is not something I'm going to ask you to do, but if you wanted to calculate it, it would be mu naught times the current induced divided by 2 pi r, the distance from your point to the wire, and the direction would be out of page. So that induced current would end up going against, or that induced magnetic field is in the opposite direction of that existing field. Okay, we're going to kind of tighten all that up and look at it in a couple of laws when we get to it. But you see, just the motion of that bar does a lot of stuff, right? It makes it move, which makes a current, which makes a field, which makes a potential. There's our current, it feels a force, and that current also makes a field. So a lot of stuff happens when you move in the magnetic field. Let's look at a demo of this. So the demo we'll look at specifically is the fact that that magnetic force, the induced magnetic force, opposed the motion. It tried to stop that bar. So this one back, this one up. So these are just 2 little pieces of aluminum bars. They're freely swinging, close to freely swinging. They are not magnetic, so they're not attracted to my rare earth magnets, not at all. So if I get them swinging, I think everybody can see it. They're swinging the same way, more or less the same period. Okay, so exactly the same way, nothing going on there. They eventually get out of sync because one of them has a little tiny bit more friction than the other, but close enough. This, a very large magnet. It's pretty heavy. And I'm going to take it and I'm going to put it so that one of these bars will swing freely between the poles of that magnet. And remember, the bar is not magnetic at all, so it's not attracted to the magnet. Okay, so now the only thing that's different is I've got a magnetic field around that bar. Okay, so this is what we just looked at. I've created a magnetic field. I let a conductor swing in it. There was motion of the charge. The motion of the charge made an electric field, which made a potential, which made a current, and then it felt a force, and the force opposed the motion, which made it stop. So this is magnetic braking. This is good, right? Most brakes that you have are kind of physical friction resistant brakes, which is why you have to change your brake pads on the car all the time because they just wear down. You would never have to change these brake pads because nothing touching, right? Nothing wears off. And this is how they do magnetic braking in a lot of vehicles. BQ tried to tell me that my car had magnetic brakes. I'm not buying it. Maybe her car does, but mine doesn't. Okay, but anyway, you know, they use this. I guess they use this in a lot of the fast trains and stuff because you don't want those relying on friction brakes.
Especially the monorails.
Yeah.
The electric current.
I don't know how you can say monorail without singing it. But yeah, that's a really good application, right? So magnetic braking is where we can see this happening. Okay, questions? Okay, let's come back to your question now. You said the magnet wasn't changing, so let's talk about that idea and what had to change. So the magnetic field in the area had to change, right? The strength of the magnet going through that loop of wire, that was the thing that had to change, how strong the field was. So let's remember our definition of electric flux. That was the electric field, the number of electric field lines cutting through an area, and we did the scalar product between electric field and area. So that was something we did there. We can also define magnetic flux. It's the number of magnetic field lines cutting through an area. So it's the same idea, we're just using magnetic fields here instead of electric fields. Magnetic flux, it's B dot A. So B times A times cosine theta. If B is changing or A is very weird, you would have to do the integral. We're not going to get into those integral cases, but it's kind of good to know that you could if you had some sort of strange situation. Let's see, this theta is an angle between the magnetic field and the area vector. The units of magnetic flux are called Webers. I don't know if that's after a German person or not. I'm going to have to check. If it was German, it's probably pronounced Weber. I'm going to have to see. I'm going to say Weber. That's got a symbol of WB, and 1 Weber is a Tesla times meters squared. So just like electric flux, if your area is straight up, if it's perpendicular to those field lines, you get the maximum flux. As you start to tilt, the flux reduces. When your thing is parallel to the lines, you don't get any flux at all. So that's the same as all the electric flux stuff that we did. Let's do an example of magnetic flux so that we know how to use it. So the figure is a 3D view. We've got a flat surface. It's got an area of 3 square centimeters. It's in a uniform magnetic field. We know the flux in milliwebers. Find the magnitude of the magnetic field and show the direction of the area vector A. So this is very close to all of those electric flux examples we did. Right off the bat, I think I'll draw a side view of this rather than the 3D view. So in our side view, our surface is at a slant. I can put my angle in there. So here's the horizontal. This angle is 30 degrees. We remember that area vectors are perpendicular to the surface. So there's our area vector, stick straight out. We're asked the direction of the area vector. We can say perpendicular to the surface. We can also draw that area vector on our page. So if I drew another horizontal line right here, this angle would have to be 30 degrees, which would make this angle 60 degrees. Everybody okay with that geometry? So these are 2 parallel lines. Those internal angles have to be the same. The A is perpendicular to the surface, so if that one's 30, that has to be 60. So that shows the direction of the area vector. Our magnetic field vector was parallel to the surface. So I'll draw that one in there. That's our B. It's talking about flux, so let's write down our equation for flux. Magnetic flux is B dot A, B times A times cosine theta. We're trying to solve for our B, so B is going to be the magnetic flux divided by A times cosine theta. The only way to make this hard, really, is to give the flux in milliwebers, so you have to deal with the millibits. To give your area in square centimeters, so you got to convert that to square meters. And to recognize that the angle is between B and A, so you can't use the 30 degrees in the picture. You have to look at your diagram and look at the angle between B and A. So it's kind of the only way we can make this difficult here. It's just not that hard a problem. So our magnetic flux is 0.90 milliwebers, so that means 0.9 times 10 to the minus 3 webers. Our area is 3 square centimeters. So to do that conversion, you have to multiply by 1 meter divided by 100 centimeters. That'll take care of 1 centimeter. You got to do it again to take care of your centimeters squared. That gives us 3 times 10 to the minus 4 meters squared, and our angle theta is 60 degrees. So there's all the ingredients for our equation. When we work it out, we get 6 Teslas for the magnetic field. So let's come back to Faraday's effect, and we'll write down Faraday's law. So Faraday's effect was the fact that we saw an induced potential and an induced current when we had a change in something to do with what's going on. We changed the motion of the bar, that induced stuff. In our demonstration, we changed something about the magnetic field, that induced some stuff. So Faraday's law, or Faraday's effect, will state that we get a current and induced potential, sometimes it's called motional EMF. We see that when we get a change in magnetic flux. So that's Faraday's effect. Faraday's law tells us about the induced potential. So we did the special case of the moving bar. Our general situation is that the induced potential is negative change in flux divided by change in time. If you had your flux, B times A times cosine theta, if that was some sort of function of time, 12 times t squared plus t, that's when you'd use this derivative form. If you just had a couple of numbers, you would do your induced potential is the change in magnetic flux, delta flux over delta t. So just like in physics 1050, velocity was the derivative of position with respect to time. If you had a function, you do the derivative. If you had 2 points, you just do delta x over delta t, sort of the same deal here. So this is for the general case. The negative sign here, your book refers to the direction of potential. I don't agree with that. Potential is a scalar quantity. It doesn't have a direction, but your book does talk about it. This negative sign here, what this means is that the induced potential is created to oppose whatever change we make in the magnetic flux. So just like we saw that force on the slider opposed the motion, the induced potential will always oppose the change. That's what that negative sign is telling us. You can't say induced potential is left or right, just like you can't say temperature is left or right. That doesn't make any sense. Okay, but you can say temperature goes up or down. It kind of means the same thing here, right? So our induced potential opposes the change in flux. So typically, and the things I'm going to do, we're going to use Faraday's law. We'll use this idea and find the magnitude of the induced potential. And we're going to use Lenz's law that goes with Faraday's law to tell us about the directions of the vectors. So the directions of the induced currents and the induced fields. Okay, everybody still with me? So let's see if this has happened to anybody before and see if you know why. Anybody plug in or unplug iron, computer, something like that and see a spark? This is Faraday's law. This is Faraday's effect. So your computer is plugged in and you unplug it. As you unplug it, you're breaking the circuit, right? So there was a circuit between the outlet and the cord to your computer. You unplug it, you break the current, you turn off the current. Changing the current changed the magnetic field because there was a magnetic field around the power cord to your computer. You've turned off the magnetic field because you unplugged it. Faraday's law says we will induce a magnetic field to oppose that change, right? So you get an induced current, an induced potential, and an induced field. Because there's an induced potential, and it happens between your cord and the outlet, there's an induced potential difference across that gap. That potential gets large enough that the field is big enough, the electric field gets bigger than 3,000 volt or 3 million volts per meter. That causes the dielectric breakdown, which makes the spark, which is what we saw with the Van de Graaff machine. So it's the same thing that happens, right? You unplug it, you break the current. Faraday's law says, no, 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 not so fast. It induces the new field and the new current, and you actually get a current jump between the plug and the outlet because it's trying to maintain that current.
So in that situation, we induced the current and magnetic field on the plug/wire, right?
In the air between the gap.
In the air between.
Yeah.
Right.
Yeah, cool.
But I always thought that just meant you had a poorly wired up plug.
Nope, not a thing wrong with your plug. That's just physics.
This one.
Yeah. So anytime something sparks, that's Faraday's law. Let's see. So this is just a fancy picture. I took it from a FET experiment, a FET simulation. If you Google FET Faraday's law, it'll let you push a magnet in and out of these coils. It'll let you see the light bulb turn off and on. It's what we did here with this galvanometer. So if you want to try it yourself and see the effects of changing speed and all that stuff, by all means. And then I wrote down Lenz's law. I've got that on the next page as well. So I think I'm just going to switch to the next page. So we went through all that slider business. We talked about the direction of the motion of the charge, telling us about the direction of the induced current. It let us see the potential, see the electric field. We got to think about the direction of the induced magnetic fields. It's a lot to think about, and you can sum it up in Lenz's law so that you don't have to go through each of those individual steps every single time. So Lenz's law says we will get an induced current. It has to be in a conducting loop, right? So you've got to let the current flow if the magnetic flux through the loop is changing. So we have to change the flux. To change the flux, you can change the strength of the field, you can change the area that the field is cutting through, or you can change the angle between the field and the area. So little generators, the coils spin, that changes the area, right? So that's how a generator works. The direction of the induced current is so that the induced magnetic field opposes the change in flux. It's all about the change. So you can think of it, and this is kind of how my first year physics professor explained it to me, is that nature does not like a change in magnetic field. Anytime we change the magnetic field, nature will create a new magnetic field to oppose that change. It will always try and keep it the same. Okay, what we mean by nature, who knows, just some sort of physics that's out there. So the physics of the situation says that the magnetic field, we will always try and oppose the change. It will be created to oppose the change. So let's go through a little set of examples to see if we can understand how that works. So let's take a simple one. I've got a conducting loop right here. Oh rats, I forgot to bring my roll of tape. Okay, so here's my conducting loop. And I've got a bar magnet right here. So what I'm going to do with my example is I'm going to push my bar magnet closer to the loop. So this is what I'm doing to the loop right here. So let's think about what's happening. We know that magnetic field comes out of the north end of a magnet. So that's the existing magnetic field. If we push it closer, let's ask, what does that mean? So if I push it closer, I'm putting the loop in an area with a bigger magnetic field that points upwards. Does that make sense? I'm putting the magnet closer. The field is stronger close to the top of the magnet. So I've increased the amount of magnetic field that it's sitting in. So increase the points up through loop. So that's the change that I did. Lenz's law says we are going to get a new field that opposes that change. So if I've made it bigger pointing upwards, the induced field is going to have to point down, right? It's got to cancel some of that new field out. That make sense? So we will induce B down. So I make B bigger up. The change would be to make a B pointing down so that some of that cancels. So then the induced field will look like this. Okay, it needs to oppose that change. Let's think about what does that mean about magnetic field. Here's our current, induced current. So I've induced a field that points down through this loop. So I know with my right-hand rule, my thumb is my current, my curled fingers are my magnetic field. I've made magnetic field through the loop pointing down. So I'm going to get a current going through the loop in the direction of my thumb, right? So my field points down through the center. I'll pretend like I'm grabbing my loop here. So my fingers are going down through the center. So my current is coming this way across the top and comes around through the bottom. So this is going to be our induced current. Makes sense? Hopefully. So let's try this one. What if we pull the loop away from the magnet? So what if I lift the magnet up? Anybody want to take a stab at what they think happens?
The B induced and the current induced are just going to be the opposite direction of what we just considered.
Okay, and are you just saying that because you've reasoned it out or because it's sort of an opposite behavior?
The second thing I think, because it's the opposite behavior of what we just studied.
Yeah, okay. So you're right, it is going to be the opposite, but why don't we go through the process? Okay, because on the exam, you're not going to have number one to say it's the opposite of number one. So as it stands right now, my magnetic field points up, right? It points up and it's whatever strength. If I move the loop away, the field still points up, but it's not as big anymore, right? I've moved it to an area with a smaller magnetic field. So the magnetic field points up. There's our B, which is created by the bar magnet. If I pull the loop up, I decrease B, which points up through the loop. So if I've decreased B pointing up, the way to oppose that change, the way to get the field to stay the same, is to make some new field that points up. So my field has gotten smaller. If I want it to stay the same, I have to put a little bit more field in. So I have to induce a B that points up to get it to stay the same. If my magnetic field points up, I have to ask, what does that mean about my current? So my fingers are my magnetic field. I'm putting them through the center of the loop, because the field points up through the center of the loop. Putting my thumb on the front of the loop here, I'm asking, what does my thumb do? My thumb points to the right, so my current points to the right. There's my induced current. Okay, and then maybe I'll just say, think about this one as best you can, get an answer for this, and we'll open Friday's class with this one.